I think we can get started. Today we are going to go through the variational autoencoders. So let's first make a brief review of the autoencoder. So for the autoencoder, the output is the input itself. It is to minimize the mean square error or mean absolute error, and we just need the output and the input. And autoencoder learns a compressed latent representation. By compressed, it means the dimension of the latent vector z is smaller than the dimension of the input vector x. So we want to say that linear single-layer autoencoder performs PZA. So here linear, it means we do not have a nonlinear activation. And recall that in PZA, we have x hat is W transpose x. So actually W is the covariance matrix of X in PZA, and here W is the parameter matrix in the encoder or the decoder. And actually it is not a PZA because the parameter matrix W is not symmetric in reality. And the parameter matrix W does not have to be the transposed matrix of the matrix in the encoder. And if we want to make the autoencoder deeper and add some nonlinear activations, some powerful representations can be learned. Yeah, so why using autoencoder? Because it learns a compressed latent vector, which keeps the most important information of the input data. So for some applications like the image denoising, let's go back to this figure. So here, we want to input the summation of a clear image and some noise, and we are expected to generate a clear image. And here, this x hat is reconstructed from the combination of the clear image and some noise, and x here, we still use a clear image. And neural machine translation. So neural machine translation borrows the idea of autoencoder. The idea is that, yeah, it has an encoder, it has a decoder, and the encoder learns a representation. So you should be familiar with that if you have started with homework for part 2. So what are some drawbacks of autoencoder? Yeah, autoencoder easily achieves zero reconstruction loss on a specific limit data set. So its generalization ability is not guaranteed. In addition, it is challenging to generate a new data point. So here, let's say, once this model is well trained, and then if we just remove this encoder, so we just hope to feed an input vector z to the decoder and to generate a new data x. So the thing is, how do we sample little vector z? So how do we select z? Actually, typical, it is challenging. Then, let's come to a variational encoder. So in VAE, we would expect to create an image of a data point from a distribution. So the variational encoder learns a distribution. So most straightforward example, we have a couple of images and we want to learn the probability distribution Px. So here X represents an image. To be specific, we can just flatten each image matrix into a vector. And then, so here X corresponds to the vector. So the question is, how do we learn distribution over these 4 images? Yeah, we can first assume that so this image vector just follow the Gaussian distribution. And then by applying the maximum likelihood estimation, we can compute the mean and the covariance matrix just using these four vectors. Then I think we have the distribution Px. So later, if we want to generate an image, we just sample a random vector from this Gaussian distribution, and then recover the image matrix from this vector. So the thing is, in most cases, this is incorrect because in reality, we do not know the real distribution of the image. So perhaps this assumption is incorrect. So although the central limit theory indicates that the vector will follow the normal distribution once there are infinite number of image data sets, but here we just have limited data. And as you can see, once we are computing the covariance matrix, in most cases, this x vector is high-dimensional vector. So this computation x minus mu times x minus mu transpose, it is really computing less efficient. So we want to switch to some other methods to compute the probability distribution px. So imagine that we have a latent vector, which is a compressed low-dimensional latent vector, and we hope to generate the image from this latent vector. And we also assume that we have a prior distribution of PZ, and at the meantime, if I have the conditional distribution Px given Z, then the image can be reconstructed from the PZ because Px is the integral of Pz times Px given Z. The issue is that, so although the Z is a low-dimensional vector, it is still a high-dimensional vector actually, because dz here is, you can written it as dz1, dz2 until dzk. So computing this integral is still time-consuming. Then, so variational encoder will resolve this issue. Let's look at this joint distribution. So in the variational encoder, we have encoder, we have decoder. So some details will be mentioned later. Let's say this is a decoder. So PZ is given in advance, and it is just determined by yourself. And X given Z, which is a conditional distribution. It is also known because in the decoder, if we have a Z, then we will generate an X. So this X can be regarded as a sample from the distribution Px given Z. And in the statistical learning, this is also called the probabilistic decoder. So this decoder can be regarded as distribution Px given Z. So Pz is known, Pz is given. Px given Z, perhaps it is not known because we do not know the specific expression of this formula, but Px given is known. The thing is, Px is not known. That is our goal. We need to compute Px, and Pz given x is also unknown. So we want to say that in variational encoder, we just want to make Px given Pz given x be close to Pz, and thus Px will be close to Px given Z. We will mention the details later. So this is called variational inference. Variational inference is a definition proposed in the probabilistic graphical models. That is just to compute the Pz given x. So here is a basic architecture of variational encoder. Similar to autoencoder, it has an encoder, it has a decoder. The difference is that instead of generating a latent vector Z, the encoder generates a distribution. This distribution is actually called the QZ given X. We will discuss it in detail later. So let's look at this figure. We want to fit some images into the decoder, and we generate a distribution, which has a mean mu and the covariance matrix of sigma. So we want to denote this as QZ given X. Why? Just as mentioned before, PZ is given and PX given Z is known. So PX is unknown and the PZ given X is unknown. So the thing is, we do not know the expression of PZ given X. So PZ given X is unknown. We just use the QZ given X to simulate the distribution of PZ given X. So the reason that we denote it as Q is that it is just an approximation of PZ given X. Yeah, so the output of encoder is just a distribution QZ given X. And we then sample random vector Z from this distribution and fit this distribution Z to the decoder. So actually, this is a constraint. We want to make this distribution QZ given X be close to the prior distribution PZ as much as possible. So yeah, actually, the joint distribution indicates that Pxz is Px times Pz given X. Here, we can just replace Pz given X by Qz given X because Pz given X is unknown. We have to compute the Qz given X. Yeah. So actually, the output of encoder here for the covariance matrix, it is log sigma square because we expect the output of a neural network to be any real number. So that's the reason why we take the log of the covariance matrix. So the thing is, we just indicate this mu, this log sigma square, represent the distribution of QZ given X. But how can we guarantee this is close to PZ given X? So yeah, in variational encoder, we already know that there should be a loss function, that is the reconstruction loss. So what is the other term? The other term is just to make these two distributions be close to each other as much as possible. So let's continue with this. We need a loss objective, that is to minimize the distance between two statistical distributions, Px and Qx. So here, Px is Pz given X and Q is Qz given X. We will use the KL divergence. So what is KL divergence? So first, we mentioned that we will define information which is minus probability. Here, X is an event and Px is the probability that this event will happen. So the larger the probability, the smaller the information. So if an event is impossible to be happening, then it contains a lot of information and vice versa. And the entropy is just the expectation of the information. So these are all defined on the discrete variables. And for the non-discrete variable, we just take an integral here. And KL divergence of P and Q is defined similar to the entropy. So note that KL divergence over P and Q is different from KL divergence over Q and P if you observe their formulas. So we will call this term the KL divergence with respect to the P, and we will call this term KL divergence with respect to the Q. If we just want to minimize the distance between Px and Qx, here we can just randomly pick one because, yeah, they have the same goal. So the first lemma is that any KL divergence is non-negative. And we just take the Jensen inequality. We will find that the minimum value of KL divergence is just 0. So this is important, and this definition will help us to define evidence lower bound. Yeah. So let's come back to this figure. So here in the variational encoder, we still need a reconstruction loss. Perhaps we need a mean square error over x and x hats. And we also need a loss objective so that we want to make the approximation distribution QZ given x be close to the real distribution PZ given x. Again, so in the whole model, PZ is given, PZ is known, and PX given Z is unknown. And PX is unknown, and PZ given X is unknown. So we hope to generate a distribution QZ given X so that QZ given X is known, and the QZ given X is the approximation of PZ given X. And finally, every item should be known, so PX can be solvable. And let's continue with this constraint, this loss objective. So we just perform the KL divergence over PZ given X and QZ given X. So yeah, you can written it as KL just with respect to the P. And here we just take the KL divergence with respect to the Q. It doesn't matter too much actually. So it can be written in this formula. And if we then apply the Bayes rule on the PZ given X, we will get just replace this PZ given X by PXZ over PX. And then we just separate this PX and we'll get this term. So we will get that we just move the log PX to the left and move the KI divergence to the right. So finally, we will get log px is ki divergence plus a term. So let's continue with this. So as we can see, px, so although px is unknown, it is a fixed distribution. You can regard it as a constant distribution. And ki divergence is still unknown. So we need to minimize this term. We need to minimize the ki divergence between q is given x and p is given x. And the thing is, PZ given x is unknown. So this term is not solvable. This is intractable. We cannot compute this. So in other perspective, we have to compute this term. So we would call the latter term as the evidence lower bound. The reason is that Ki divergence is always non-negative. That means log Px is always more than or equal to this term. So in this term, QZ given X is long because it is the output of the encoder in the VAE. And PX given Z, yeah, we will figure out this term. So this term is tractable if PXZ, if the joint distribution is tractable. So again, because log PX is a fixed distribution and this term is unknown, we need to minimize this KI divergence because we hope the generated distribution QZ given X be close to the real distribution PZ given X. We have to maximize this term. So this is our goal. And this is the evidence lower bound. So in the VAE, our goal is just to maximize the evidence lower bound in addition to the reconstruction loss. Yeah, so again, variational encoder is a generative model, and we model the joint distribution of x and z, which is px times pz given x, pz times px given z, and pz is given, pz is known, and px given z is known. The thing is, these two terms are unknown. Then we just generate a qz given x from the encoder. So that's we hope this is the approximation of pz given x, so that pz given x is known. Then everything's solvable. And later on, so to make these two distributions be close, we will use the KL divergence, and we derive this formula. And since this KL divergence term is intractable, we will focus on the evidence lower bound. It is the evidence lower bound because this term is always less than or equal to the log px, which is a fixed distribution. Okay, so let's continue with this. So I think we can start with the joint distribution pxz. Yeah, similarly, we just apply the Bayesian rule. We just replace the px z by the px given z times pz. And yeah, just separate px given z here, and we are getting this term. And here we can see the latter term is actually the ki divergence between qz given x and pz. So what is our first term? We can written it as an expectation form. So the first term is actually the reconstruction loss. So here in the variational encoder, we have input x and we have the reconstructed data point x hat. Actually here, this x in reality corresponds to the x hat, and this px given z can be approximately equal to px hat given z or px hat given x. So this term is actually, this is a negation of the reconstruction loss. our goal is to maximize this term. So we need to minimize this term and maximize this minus KL divergence or minimize this KL divergence. Yeah, so this term corresponds to the reconstruction loss, and this is KL divergence over QZ given X and PZ. We want to say this is tractable because QZ given X is null. Why it is null? Because it is generated from the encoder, and PZ is null because it is defined by yourself. In most cases, we will just use the standard Gaussian distribution as PZ, but it depends. So the loss objective is just the negation of this evidence lower bound. So we just need to minimize this term and minimize the KLA divergence between QZ given X and PZ. So the other loss function is the reconstruction loss. So the final loss function in the variational encoder is this term plus ignore that. So this is only this is just the reconstruction loss. This is the only loss function in the variational encoder. Sorry about that. Yeah, so we get the loss function of VAE. Yeah, so let's come back to this figure. Have some image as inputs, and we pass them to the decoder to the encoder, and we generate the mean and the covariance matrix, which is the distribution of QZ given X. And by applying the loss objective, the QZ given X will be approximately equal to PZ given X, and then we just sample a latent random low-dimensional vector from this distribution QZ given X and feed Z to the decoder, and that generates the reconstructed image. So this is the whole idea of VAE. And then we have some discussions here. So first, let's come back to the formula here. Our initial goal is to make the QZ given X be the approximation distribution of PZ given X. The thing is, it is intractable because PZ given X is null. And then in the final loss objective, we actually minimize the KL divergence between QZ given X and PZ. So finally, we in reality minimize both these two terms. So we minimize the KL divergence over QZ given X and PZ, and between QZ given X and the PZ given X. So finally, we should expect that QZ given X should be approximately equal to PZ, should be approximately equal to PZ given X. If we predefine so a prior distribution PZ, for example, that is the standard distribution, then finally this QZ given X should be approximately to a standard Gaussian distribution, and the real posterior distribution PZ given X should be approximately equal to the standard distribution. So here we will indicate that PZ is the prior distribution, which is defined by ourselves, and this term is the posterior distribution. PZ given X is a posterior distribution. So if we just use the standard distribution as the prior distribution here, we can derive the KL divergence between, so here, n mu sigma square represents the QZ given X because mu and sigma square is generated through the encoders through the neural network. We can just compute the KL divergence over these two distributions, and here, this is the loss function. So the final loss function could just be the reconstruction loss and the KL divergence term. So every term is tractable, and so finally everything is solvable. So this is the whole idea of variational autoencoder. We also have some other discussions here. So let's look at this specific loss function. If this loss function, we would expect that the loss function reaches 0. So we would expect both the reconstruction loss achieves 0 and the KL divergence term achieves 0. So perhaps ideally, this QZ given X should be equal to PZ and should be equal to PZ given X. So what does it mean by PZ is equal to PZ given X? It means that they are independent. So it means PZ and the joint distribution PZX is PZ times PX. And what does it mean? So we want to indicate that this is undesired. Why? Let's look at this figure here. We generate a mean and we generate a convergence matrix of QZ given X. So this is QZ given X. Actually, this figure is incorrect. Why? Let's look at this. It should be kind of like this. So imagine that this is within a media batch and the batch size is 4. We have 4 data points, we have 4 images, x1, x2, x3, x4. So for each image, we will generate a unique mean, which is mu1, and a unique convergence, log convergence, that is log sigma 1 square. So this distribution is, this is Q zi given xi. This corresponds to the P zi given xi. So I want to say that this distribution is only specific to this data point x1, and similarly, x2 generates the distribution mu2 and sigma 2 square, and this distribution qz2 given x2 is only specific to the data point x2. And then, so if we wanted to reconstruct the image x hat, x1 hat, we have to sample latent factor z from this distribution, rather than rather than sampling the data points in the second distribution. So to be specific, we have to sample a latent vector z from distribution which has a mean of mu1 and the convergence matrix of sigma 1, rather than the mean of the mean 2 and the convergence matrix of sigma 2 squares. So the reason I want to mention this is that so z and x are not expected to be independent with each other. So they should be dependent. So actually, there is a contradictory. So there is a trade-off because let's just go back to this term. The reason we want to minimize the KI divergence between QZ given X and PZ is that let's come back to the previous loss objectives. So the reason we want to minimize this term is that we want to minimize the KI divergence over between QZ given X and PZ given X, because we just want our generated distribution be the approximation distribution of PZ given X. But once this QZ given X is approximately equal to PZ given X, then X tends to be independent of Z. So so to be specific, we don't expect this term to be as small enough. We do not hope it reaches 0. So actually there's a trade-off. If we expect to reconstruct a high quality image, then perhaps this term should be large. So in most cases, once the reconstruction loss is small, sometimes the item, the KI divergence item, perhaps should be large. So this is how thing. And the last discussion is the reparameterization trick. So here, let's look at this figure. The output of the encoder is a distribution rather than a latent vector z, and then we need to sample z from this distribution and feed this z into the decoder. So we want to guarantee that every part in the neural network is desirable. So we hope these parts can be learned. Then how do we guarantee this? We will use a reparameterization trick. Imagine that we want to sample a data point from a distribution of mu and sigma square. We first sample data point from a standard distribution, and then we just perform the linear Gaussian. That means so we just times the sigma, the standard deviation, and plus the mean, and then we will get sampling latent vector. So let's come back to this figure. This is the variational encoder. So the input is the image itself, and the output of the encoder is a distribution which has a mean of mu and a covariance matrix of sigma. This is the distribution of qz given x. We hope this to be approximately equal to the pz given x. And actually, as derived beforehand, it is intractable to compute the KL divergence over pz given x and qz given x. We have to instead compute the KL divergence over qz given x and pz. So here, this standard Gaussian distribution is pz. And then we will sample latent vector z from this distribution. So we will use the reparameterization trick. We first sample a data point from a standard distribution and then perform the linear Gaussian. And so pass the z to the decoder, and we will get the reconstructed image. And again, so here the batch size. So if we just assume that the dimension of the mean, for example, it is d, it is actually a matrix with a size of batch size times d. So here, for each image within the media batch, the encoder will generate a specific distribution qzi given xi, which uniquely corresponds to the input image xi. So that's, we can note x and I. We cannot expect x and z to be independent with each other. This is the whole idea of the variational encoder. So different from the autoencoder, it will generate a distribution qz given xi, and then every term, including the px, is solvable, so that we can generate everything. So once this model is pretty well trained, then we can just remove the encoder and sample latent vector from a standard distribution. And then reconstructed image can be expected to achieved. So this is the basic idea of variational autoencoder. I think later Akshay Gupta will go through some coding part. Yeah. So before moving to the next step, does anyone have questions regarding the concepts of the variational autoencoder?
I had one question about mu and sigma of x. So these are going to be, we decide exactly what shape we want to encode to, right? So then we know mu of x should have some shape, and sigma will follow that. But how do you decide how much to encode to, like 2 versus like an integer or some n-dimensional vector?
Okay, so actually, in a variational autoencoder, so in the most simple model, this mean and variance. So as I mentioned before, this mean is a matrix with a size of batch size times the dimensional d. So this dimensional is equal to the dimension. This dimension just corresponds to the dimension of the latent vector z. So if we just define the dimension of z as d, then this mean should have a dimension of d, and this conventional matrix should have. So actually, this conventional matrix should have a dimension of d by d, but just to be simple, we will make assumption that this is just a diagonal matrix. So actually, this is the vector here. Yeah, so that can be regarded as a hyperparameter. That is actually the in binding size. You can regard it as that.
Thank you.
Yeah.
And could you just go over briefly again what's the purpose of this autoencoder? Like, I know like it kind of like crashes down dimensions, but what was I think I missed like the meaning part a little bit. Like, how do we use it? Like, or more on the conceptual side? Do you mind reiterating that again?
So I'm sorry. So which parts are you referring to?
So I think you mentioned in the beginning how it's kind of a good way to sorry, I kind of missed it, but like
Yeah,
like
it's fine. It's
represent
fine.
the picture, like yeah, it's like a compressed latent representation. And do you mind like going like just like extending a bit more from that, like why
I
would
think it's something I'll go through. So my aim
oh
would be
okay,
to
sure.
tell you the difference between an autoencoder and a
Yeah,
variational autoencoder.
yeah,
So maybe
thank
wait
you.
Okay,
for a
cool,
second.
cool. Okay, thanks,
Yeah, Jack.
Aksha.
Mhm.
Okay, yeah. So I'll 1 second. I'm just trying to set up here. So wait, can you hear me twice?
Yes.
Yeah. Sorry, guys. Give me a second. Okay. So I hope you can see my screen here. So yeah, quickly going through what an autoencoder is, and then I'll show you the code for it, and then a quick iteration through what a VAE looks like. And my aim would be to highlight the difference between what an autoencoder is and does, and what a variational autoencoder is and does. So a general structure for an autoencoder is something that we've seen already, but just quickly going through it. We have an encoder network, we have a decoder network, and we have a latent variable whose dimension we choose ourselves. And the way we train it is that, say, for example, the example I'm going to show you is of MNIST images. So we input an MNIST image, and the output image we get, we expect that to be exactly same as what we input. And applications to it can be finding a compressed representation of the MNIST image, for example, that we send in, or like finding the most important features. So, for example, if you want to send uh, not the entire image through a classifier, but like the most important parts of the image in terms of a feature into a classifier, you could find a latent representation which is nicely able to represent the image, and which is like some form of an embedding of the image, and send it to your classifier. And what we want to minimize here, what our objective is to oops, to minimize the mean square loss between what was reconstructed and what was put in. So that's basically an auto encoder. And here's quickly going through the code for an autoencoder. It's very simple. The encoder network is what I've done here is like are just 3 linear layers. You can put a convolutional layer in here, and I have compressed. So my latent vector here is of dimension 10, which is like a natural dimension to choose if you're dealing with MNIST images. So the encoder compresses the input image to a 10-dimensional feature vector, and the decoder reconstructs the image from the latent representation. Here, the forward has 2 parts. One is, so we're not always, after training the model, we're not always using the encoder. Sometimes we just want to encode the image. Sometimes we just want to use the decoder, which is why I have a flag here for encode. So while training, we're training both of them simultaneously. So we use both. And when the model is trained, sometimes we just want to encode, sometimes we just want to decode. So this is this is a very simple implementation of an autoencoder, and loss we use here is the mean square loss. And I'm just going through the iterations here. Yeah, and here I'm just storing the representations for some of the images from 1 to 10, and this is kind of what I get back. So, for example, this is the original image that I sent to the autoencoder, and this is the image reconstructed from the 10-dimensional vector representation. So this was an autoencoder. Just so we didn't show the code, I think, in too much detail last time. So just showing you that, and also hopefully this will help in identifying the difference between a VAE and an autoencoder. So next, let's look at what a VAE does for us. Okay, so getting back to, I think, Hyun's question, and hopefully I am able to answer what you asked, but let's start again. Just an overview of what a VAE does. A VAE is a generative model. What is a generative model? In a generative model, we try to model the distribution from which our data set comes from. So whatever data set we're given, we want to be able to find the distribution from which our data set is coming from, assuming that our data set is typical of the distribution from which our data set comes from. Now, to be able to do that, let's say our data set is, so to be able to do that, we want to find 2 functions, as Jiachin showed. We want to find the function p of z given x, which is the function that generates the latent variable given the input data set. And we want to find the function or the distribution p of x given z, which should generate an output image given a vector in the latent space, or given a point in the underlying latent distribution. Now, these are the 2 things we want to approximate, or we want to find out. Now, p of z given x and p of x given z are 2 functions we want to find out. So what can we use to find these functions? There's a little thing you guys might have studied called neural networks, which are great function approximators. So we use neural nets to find both these functions, and we have to find both of them together. It's kind of like a chicken and egg problem, that the way you go from the data set and find the distribution, you need to know that information to be able to generate the image out of the distribution you found again. So we need to find both of these together. And that's why, again, in a variational autoencoder, we have two blocks. One is, again, an encoder, and one is, again, a decoder. Here we try to recover the image given a latent vector. And in the encoder, we're trying to find this function, a mapping from the input image to the underlying distribution. Now, as Jasmine pointed out, finding P of Z given X is not a tractable problem. So what we do instead is we find a function Q of Z given X, and we make it such, we find it such that it's as similar as possible to P of Z given X. So a very coarse overview of what we do in an autoencoder or a variational autoencoder is, first of all, we're trying to find the distribution that corresponds to, that generated the data we have. And yeah, we're trying to find the distribution that generated the data we had. And to be able to do that, we wanted to find P of Z given X, which is the latent vector or the distribution given our data set. But that problem is intractable. So what we do is we convert it to finding a function Q of Z given X, which is whose form, which is a distribution whose form we choose. For example, in our case, we choose a Gaussian distribution, and we find Q of Z given as X such that we minimize the KL divergence between Q of Z given X, the KL divergence between Q of Z given X and P of Z given X. So basically, we want to say that we find Q of Z given X such that it's as similar as possible to P of Z given X. Now, as Jatin showed in his derivations, what happens next is we do some math, and we again convert this problem to finding, again, Q of Z given X such that we're maximizing the elbow function, which is something probably just an intermediate step here. But yeah, so we convert the problem to this. And finally, what we end up doing is, again, after doing a bit of math, we convert this problem to saying that we want to find Q of Z given X such that we minimize the loss function, which is Q of Z given X, which is the KL divergence between Q of Z given X and a probability distribution of the latent vector which we choose. And we minimize the kind of maximize here something similar to the log likelihood of our data set. So this is something, this loss is something we want to minimize. So that's basically our loss function. We go from finding P of Z given X to wanting to finding Q of Z given X such that this loss function is something we minimize. And again, what are we doing here? We're trying to find the underlying distribution that generated our data. And how is it different from an autoencoder? So here we're dealing with distributions. So what we want is to be able to generate let's say, the distribution from which we can draw samples from. So in the encoder part, we want to generate the output of the encoder should be the parameters of the distribution, of our underlying distribution. And what the decoder takes in is a vector from the underlying distribution. And the power that the VAE gives us is that we can choose the form of the distribution, which makes the problem tractable. So what we do here, what I'll show you in the code, what we're doing is we choose that the latent distribution is Gaussian, and it has a zero mean unit variance, and what the encoder generates is the parameters of the distribution, u of z given x. So what are the parameters of a distribution? Their means. So for example, if I choose a 4-dimensional latent space, so what my encoder should generate is the means of a 4-dimensional vector space for 4-dimensional distribution. And we also assume that the covariance matrix of the distribution is diagonal. So again, the covariance matrix is also characterized by just 4 variables, the diagonal variables. And yeah, so this is what we expect the output of the encoder to be. And then this basically characterizes our distribution. And then we sample from this distribution, take one sample out of it and send it to the decoder, which will then generate the image back, or some image. So I hope this problem construction was clear. It will become more clear if once I show you the code, but if you guys have any questions until then, let me know.
I have a quick question.
Yeah.
So when you're sampling that distribution, what you're generating some random number probably and then plugging it in so that you pull out some values, right?
Yeah.
Where does that random number go?
Into
You're
the
generating X, right? You're not generating the probabilities. You're generating the X.
wait, so sorry, I lost the diagram, but so we get a distribution out of the encoder. We get the parameters of a distribution out of the encoder.
Yeah.
This we sample and generate a random number of like the d-dimensional number. So we get a d-dimensional random number. Yeah, we get a number from here. So can you repeat a question now?
Yeah. So I was just trying to do that in my head, like pass that random number. Oh, never mind. I think I understand. And I'll try to figure it out. If I don't, I can ask later.
Yeah, so this is not a random number. This is a number. This is a point that we choose from the distribution. And this point is then fed into the decoder. Let's see if this becomes more clear.
Yeah. Thank you.
Okay, so now let's look at the implementation of a variational autoencoder. So this is, again, on MNIST dataset. This is what a VAE looks like. Very similar to the encoder, and the decoder network is very similar to what I had in almost exactly same as the one I had in an autoencoder. So what's the difference here is how we go through the network and what the network outputs. So let's go through the forward pass. That's the interesting thing. Now, again, we can use the encoder decoder components separately, which is why I have a flag here. But while training, we're training both of them together. Now, when we're encoding, I pass the input through the encoder network. And the output here, what I get out of this is, so the output here is, it's the first component of the, so what the vector here, so this is the batch dimension. The 0th comp, so it's a vector of dimensions 2, comma, the latent vector dimension. So, and the first dimension is the batch size. So the first dimension corresponds to the mean, the parameters which correspond to the mean that are generated. The second dimension correspond to the variance, or in this case, the log variance is something we generate, but it corresponds to the variance. So both these parameters, as Jyothan said, like this is done for every image in the batch, and they give you the so what's generated are the parameters of a distribution. Now, the next step is the sample from this distribution, which is something. So once we're done here, we go here, which is we sample from the distribution using the reparameterization trick, but do not need to go into detail there. Just understand that we're doing the sampling thing where we send in the mu and standard deviation, and because we had the assumption of that the matrix was diagonal, we can just multiply the standard deviation and by a random number of the same dimension because it's diagonal, and generate a sample from that distribution. Now that sample from the distribution that we got, or the parameters of the distribution that we got, we take a sample from it and send that to the decoder. And then the decoder tries to reconstruct the image, and it has a dual objective. The loss has a dual objective, as I showed and Jyothan showed in his presentation, and I did not focus too much on it, but I think the loss here is the most important thing. The loss has a dual objective. The first objective is to minimize the reconstruction error, which is this image that is generated by the decoder from the random number that is, or the number that's sampled from the distribution. That should be as similar as possible to the input image. While what we're doing here is modeling a distribution. So we want to minimize the distance between the distribution we're modeling and the distribution we want. So the loss then has a dual objective. And once the network is trained, so let's see what we have here. I trained the network. This code is available right now on the website, by the way. So let's see what happens when I send in things. So now that the variational autoencoder has been trained and we found the underlying, so the functions p of x given z, what we need to input into the decoder to generate samples is just a point on the latent space. And what I do here is that I input a mu, a mean vector, and a log variance vector. So this is my mean vector. Now I put this in. This gives me something that looks like an egg. So these images are not good because my model is not optimal. It's just linear layers. You could use a convolutional layer. You could use a bigger model, better model, but the idea behind remains the same. Now I take an input vector. I take the parameters mu and log variance, and it gives me an image out of it. The decoder gives me an image. Now, if I send in the same parameters again, this time I'll get a different image because we're not sending the same number. What we're doing is we're randomly sampling from that distribution first, and then sending what we sampled through to the decoder, and that's the output that we get. So this, in some sense, is for us generating the data that we so basically we're modeling the distribution that our input data comes from, and once we've done that, we have the power to generate more data that ideally, if your model is good, comes from the same distribution that your original data was from. And the way to do that is to send in parameters of, or send in some, well, basically sample from the distribution and get an image out of it. What we were doing in an autoencoder was recovering the image from a compressed version, say, of the image. So that's kind of the difference here. Yeah, so that was basically it. If you guys have any questions, let me know.
How much data do you need to like generate this sample to be sufficient? Like if how many images are required for just like this simple 2 reconstruction before you don't get garbage and you get something nice like this?
We definitely cannot do it with with 2 less data. So this is MNIST data set. We do have significant amount of images. So I think 50,000 images. So there is enough data here, and considering the dimensions of the images is pretty small. But it's not something that we can do on a data set that's not too big. Some of the applications that people use VAEs in, or GANs, is also something that you see next week, is data augmentation. Is one popular thing you could use a VAE for. So you can generate new data points if you're able to accurately find the distribution from which your data comes from, for which you need decent amount of data. So yeah. Any thing in chat? Okay, cool. So I hope I was able to answer Kyuhyun's questions.
Yeah, that's pretty clear. I have a small follow-up.
Yeah.
It's just like after, so basically after we do like say auto like or VAE or like AE, then we can use this new generated data to like train or like validate like we would do on normal data set. Is that like the idea or no?
Yeah, like for a VAE, yes, you're what you're modeling the distribution from which the data comes from. So you can use that to generate new data points, and people do that to generate new faces that don't exist, stuff like that. Probably. So that's kind of something else, is like you're generating new data points. What you're doing in an autoencoder is you're just generating back the data that you compressed.
I see. Yes. Okay. So like in VAE, you're always assuming that it's a normal distribution. Like, would you like assume it was something else, or you kind of just
the reason do that is because, so we had the scale divergence formula, right? Which was we wanted to see how similar two distributions are. So this is the formula for the for a Kale divergence between two distributions if we assume them to be Gaussian. Now you can use something else. You could use a Bernoulli distribution, and you'd get something else. The idea is to be able to find a closed form or an expression for the KL divergence, which we can very easily do for a Gaussian distribution, not so easily for other kinds of distributions.
I see. Okay, cool. Thank you.
Cool. So if there are no other questions, I think we can stop here.
I just remembered an application of this that I was reading about. And it was like, with physics or chemistry models, they have trouble getting enough data for certain things because sometimes they require expensive machinery to get. And so what they'll do is they'll measure some sort of characteristic of some chemical or lattice or some crystal or something, and then they'll use that to generate the distribution of possibilities using based on the components that are in that chemical, and then they can kind of generate new structures based on the distribution of possible structures of those components. If that makes, I don't know if I explained that well, but it's really cool.
Something like in data augmentation, in some sense, is like basically trying to get more data points because they're enough data. Yeah, that's pretty. And it's a very cheap way, you're saying, of getting data, because getting data otherwise is pretty expensive.
Yeah, because you might need something like a laser, like a big laser, or some expensive machinery that multiple research groups are having to share. And so if you can just spend an hour on it, get enough data, and then generate the rest of it, it's really helpful.
Yeah, interesting.
Also, sometimes the distributions, you can get to edge cases, and you would have to create certain conditions in order to measure those things. But if you might actually be able to generate certain aspects of that. I'm not sure how far that goes, but that's just something off the top of my head. But all right, thanks.